So I'm going to get started. If you don't have any other questions. So the homework was due at noon today, and then I changed it to 6 p.m. Just in general, when you work on the homework, pay attention to the deadline so that you don't miss it. All right. So this question number 5, I asked you to try it on your own. I don't know if you had a chance to look at it. So here we try to find the volume of the solid obtained by rotating the region bounded by y equals square root of x. So this function, again, is y equals square root of x. That's this red line. And then y equals 0. That's the x-axis. X equals 2 is this green line. And then we're going to rotate this about the line y equals -1, which is the dotted line. And then we're going to find the volume. So when we rotate that piece, imagine this is y equals -1. When you rotate around it, you kind of create this like a solid, but in the middle, you get a space in the middle there. So it's kind of like, so I'm going to try to draw the shape here. So the middle part, when you create it, it becomes a cylinder in the middle. This is this cylinder is hollow there, so there's no actual solid in that part. So just an empty cylinder. And on the outside, when you rotate that shaded region, you get this. I'm going to try to draw it as quickly as possible. So you kind of get this shape on the outside. So it's sort of like a bow, but in the middle, you get like an empty cylinder in the middle of that shape. But this is all solid. So on the, like going around that cylinder, it's solid, but in the middle, it's empty. Right? So that's the shape. And I'm going to try to find the volume using the method that we saw before. So we're going to kind of slice this shape using vertical slices. So if we take one slice out of it, so we sort of end up with this, that's one slice. And in that slice, in the middle there, you still have this like an empty so in the middle, you still have this like an empty circular disc that's not there from the cylinder. So that's one slice. And then this slice here has the width, has a thickness, which is delta x. So that's how thick it is if you look at it. And I'm just going to draw the slice on the side. So this slice in the middle here, it's a circular shape. And in the middle, you have another circle that's not there. So this part coming from the cylinder part, that's not there. But on the outside, you still have that solid. So this part is solid. And obviously, it has a thickness that I'm not drawing, which is delta x. So that's the look of that circular slice if you look at it from the left or from the right. So now we need to find the volume. If you recall that the volume we had to use those slices is integrating from the boundaries, let's call it from A to B. So in this case, we're integrating from left to right. And then of the area, the cross-sectional area from the slice, each slice that you take, but it doesn't matter where you pick the slice, you get the same shape, just different area. And in this case, because of the thickness, it's delta x, so I'm going to use dx, so the area should be a function of x there. So the next step is to determine what the A and the B are and what the AX is. So I'm going to find the AX first. AX is given by the shaded part of that cross-sectional disc or washer, really. So we're really looking for this shaded part. That's the area I'm looking for. Well, that area you can think about is given by the area of the outer circle with this radius and minus the area of the inner circle at this ring radius. So that's the area of that sort of the washer region. So that's a pi times the large radius. So I'm going to call it R1. So that's a large radius. And the smaller radius, I'm going to call it R2. So pi R1 squared minus pi R2 squared. We can take out a pi. So pi times R1 squared minus R2 squared. So that will give me the area that I'm looking for, the cross-sectional area. And how do we find R1 and R2? So the R1, if we look at the cross-section, it's just from the center of the circle to the most outer part of that outer circle. In the diagram I have, that's the distance from this dotted line y equals -1 to the highest point, which is the y equals square root of x. So I'm labeling, maybe I should label it with blue color. So this is the radius of the outer circle, the one in blue. That radius is just a difference from the red curve y equals square root of x to the dotted line y equals -1. So we can just write down R1. So R1 is equal to the distance from square root of x, so square root of x, to the line y equals -1, so minus -1. So that's the biggest radius, which you can write as square root of x plus 1. So that's what R1 is. R2 is the radius of the inner circle. That is given by from the dotted line to the blue line to x-axis in the green segment here. That's the radius of the smaller circle, the radius of the cylinder. So R2 is equal to, well, the blue line, the x-axis, has the function y equals 0. So it'll be just 0 minus -1, just 1. 1 unit is the radius of the inner circle. So this is R2. And if you put in there, you can find out the area, the cross-sectional area function, which is pi. The first part is square root of x plus 1, so that gives us square root of x plus 1 squared. And then the second radius squared is just 1 squared, which becomes pi times, you can expand it if you like. So if you expand the square term, so you get square root of x squared, so that's an x, plus 2 times square root of x times 1 plus 1, and then minus 1, so the 1 cancels out, give you pi x plus 2 square root of x. So this is a function for the cross-sectional area. Now we're going to put it back in the volume formula. So the volume becomes, we're integrating from a to b, and I'm going to find a and b later. The area is just pi x plus 2 square root of x dx. Now, what about the boundaries? Well, since we're integrating with respect to x, we're just looking for the x boundaries from left to right. The left boundary, which is at, if you look at the shaded region, the most left point is x equals 0, and then the most right point is x equals 2. So the boundaries of integration is just from 0 to 2. This will give you the volume if you integrate. How do we find R1 and R2? Well, like I said earlier, so the R1 is the radius of the outer circle, right? If you look at the cross section. And then if you look from the solid I have, the radius for the outer circle is just the radius, just the distance from that function y equals square root of x to the axis of rotation, the one that I'm labeling in blue. So that will be the biggest radius, the radius of the outer circle of the cross-sectional area. And how do you find the measurement, how long that is? Well, you just take the function y equals square root of x, you minus y equals -1. So that distance give me R1. And the same thing, you do that with R2, which is just the distance from the blue line to the dotted line. So that's just from y equals 0 to y equals -1. That gives you 1. So how do we get the integral from the left and the right, the boundaries for the integral from 0 to 2? Well, we integrate with respect to x. Right? That's what this dx tells us. So we integrate with respect to x. So that means the boundaries has to be x values. So now you go back to the shaded region that we begin with. That shaded region covers x values from the origin. So that's x equals 0 all the way to the green line, the vertical green line, x equals 2. So that tells you that the x value has to be between the 0 and the 2. So that's the boundaries of integration. If we integrate with respect to y, then we will be looking at the y values of the boundaries of the shaded region, but we're not integrating with respect to y. Exactly, just the length, just the length, the distance of the length to find the radius. And from here, you can integrate as you always do, and I'm not going to finish it because I don't think it's too difficult to integrate. If you pull out the pi and then you find the antiderivative of x and the 2 square root of x, they should be manageable at this point. We didn't finish. So a problem like this, it's very important you try to kind of create the shape, the solid in your head, and then try to imagine the cross sections and figure out the area from there. After you figure out the area function, it's very easy. You just put into the volume, right? Area times thickness, that's the volume of one slice, and if you integrate it, that part, you end up with a total volume, because integrals are just like a summation, summing up all the volume from each slice.
And so we're using the x-axis y instead of the y-axis.
Exactly. The reason we use an x-axis for integration, it's because when I pick a slice from this solid, that slice has a thickness delta x, so that's telling me that when I find the volume, I'm going to integrate with respect to x. So the delta x sort of equivalent to the dx. So dx represents the thickness of each cross section.
Okay.
Yeah, so that's like the hint. Any other questions on this problem?
The next step, we would pull out pi, right?
Exactly. So when you integrate, always allow any constant coefficients, because they don't get involved in the integration part. And I would recommend that rewrite square root of x as x to the 1/2, to make it easy to find the antiderivative. And for both terms, when you find the antiderivative, just add one to the exponent, divide by the new exponent. And I don't think it's that challenging. There are websites that you can actually draw the solid, but I looked at a few. I couldn't find the one that's really good. But if you dig around on the internet, you might be able to find some websites. But on the homework problems I give you, I believe some of the problems actually shows you the solid. That way it's easier to kind of have a visualization. This is not on the quiz, correct? This will be on the next quiz, which is next Thursday. All right, the next question. So here we're finding the volume of the solid obtained by rotating again the same region. This is again y equals square root of x, and the y equals 0, x equals 2. But this time we're going to rotate this solid about the axis x equals 2. So this is, we're going to rotate it about this green line. This will be the axis of rotation. So we're going to rotate about this green line 360 degrees. So you have this shaded region, but you're going to rotate it around this this line x equals 2. So again, the first thing I'm going to do is I'm going to draw the solid. So the 0 will be mapped to 4, and if this point stays, this point stays. So we sort of end up with sort of like that shape. But if you look at from the bottom, you kind of have this 3D shape. So it's actually going into the back and coming out of the paper. At the bottom there, it's like a circular shape. For this shape, when you slice it, you want all the slices to be circular, so you wouldn't slice vertically, right? If you slice it vertically, it's not a circular shape. So you have to slice it horizontally. So I'm just going to draw one slice. So that will be one slice horizontally. That's and if you want to add a little bit thickness to that, that's the thickness. And this thickness, as you can see, because the slice is horizontal, that thickness is in the y direction. So the thickness is delta y. That's the thickness.
And is the hint here that x equals 2? Or
so again,
what's the hint that we're using the delta y?
What's the hint we're using delta y? That will tell you that when you find the volume, you integrate from a to b, and then you're going to have a dy in that integral, not a dx. Because this part is the thickness. Since the thickness here is in the y direction, so we're going to have a dy there. That means the area function we're going to use has to be a function of y so that we can integrate with respect to y.
Yeah, but I'm asking, how did we know we were going to use delta y in the first place? I'm kind of confused on that.
You have to think about the slice, right? You want circular slices. When you take that, the circular slices, it has to be horizontal in this case, because you kind of have to look at the solid as if it's like a cone shape, but it's like a pointing upwards cone shape. So the only way you can get circular disc is when you slice it horizontally. If you slice it vertically, you're not going to have a circular cross section. And then since each slice is horizontal, so that means the thickness is in the y direction, right? It's a change in y. That's what the thickness is. So here, if you have a y1, this is a y2, so the change in y value, that's the thickness of each slice. So now I'm going to draw the cross section on the side. So if we look from the top, look downwards, this dotted line is corresponding to x equals 2, and we get this, each cross section is like it's a circular disc, right? There's no missing part in the middle, it's just a solid disc. And then this will be the radius that we're looking for that disc. And it's this shaded part. So let's find the area in terms of y. Well, because since it's a disk, that's no missing part in the middle. So the area is just pi times the radius squared. But what is the radius? That's a challenging part in this problem. Well, the radius we know is going to be this, from this line x equals 2 to the most left point. You can pick the point to the right if you like, but I'm going to pick the point to the left to find the distance, to find the radius. So that's the radius. In my drawing of the solid, so that distance is given from this blue point all the way to this point. So that will be the radius that I need to find the cross-sectional area. Well, how long is that segment, right? Well, that segment is given by the distance from the red line, y equals square root of x. Let me write down. Radius is given by segment from y equals square root of x to x equals 2. So that part give me the radius. And to figure out the radius, we're just going to take the function on the left minus the function on the right, because the one on the right always have a higher x value than the one on the left. But you have to be careful, it's not just, so the one on the right has x equals 2, but the one on the left, we have to figure out what the function for x is. We know is y equals square root of x. We cannot just use square root of x directly. We have to rewrite it in terms of x to use. So y equals square root of x, you can write it as square both sides. That's equivalent to y squared equals x. So we're going to have to use y squared there instead of using square root of x, because we're subtracting the x values. So that's a 2 minus y squared. That's the radius. And you can always go back to the setup. Like the setup, we want an area to be a function of y. So everything we have for the area of the radius has to be functions of y, not functions of x. So this is my radius, and I'm going to put into the area function. So the area in terms of y is pi times radius squared. The radius is 2 minus y squared. You can expand that, write it as pi times 4 minus 2 times 2. That's a 4y squared plus y to the 4th. And then at the end, we're going to take this, we're going to put it into the volume function. So we get volume is equal to integral from a to b. I'm going to figure out a and b later. Ay is pi 4 minus 4y squared plus y to the 4th dy. And the boundary, since we integrate with respect to y, we have to look for the boundaries of y values in the shaded region we begin with. The shaded region, just looking in the y values, the lowest y value is the x-axis. So that's a y equals 0. That's the lowest y. And it goes all the way to this point. That is x equals 2, so that means y equals square root of 2, because y equals square root of x. So that's a boundary from 0 to square root of 2. I think in this problem, the most difficult part is to figure out the radius. And the radius is given by the difference of the two x value, x equals 2, and the one on the left, which is given by the function y equals square root of x. You have to subtract the function on the left from x equals 2 to figure out the radius. Why did I plug in 2? That's exactly right. So when the boundaries for y value, the highest number is where the highest point of the red curve, right? So that's so this point gives the highest y value. So that will be the upper bound of the integration with respect to y. So we need to know what's the y value corresponding to that point. So you take 2, put into the function y equals square root of x, and that y value ends up to be square root of 2. So that's the upper bound of integration. Any other questions on this problem? Again, I'm not going to solve this, but if you want to finish this, bring pi to the outside and find the antiderivative of each of the terms. They shouldn't be too bad when you find the antiderivative.
Why is it the square root of 2?
Say it again.
Could you explain why the upper bound is square root of 2?
Right. So if you look at the shaded region that we rotate, right? The boundaries that we need, the lower and the upper bound, they have to be the y values because we integrate with respect to y. That's what dy tell us. And then if you look at the shaded region, just the shaded region that we begin with, that region has the lowest y value corresponding to the x-axis. So that's the lowest y equals 0, right? But then the highest y value for that shaded region is corresponding to this point that I'm kind of putting a star next to, right? So that point, will give me the highest y value. To find that y value from that point, we have to use the function y equals square root of x and the x equals 2, because that point has the x equals 2. To find the y, we're going to take 2, put into y equals square root of x. That will give me y equals square root of 2. So that's the highest y value we have for that shaded region. So we're basically having a lot of disks, that are on top of each other. Each one of them has a thickness of delta y, and you add them from y equals 0 all the way to y equals square root of 2. So that's what the integration means. Even though I'm only drawing one disk in the middle, that means, but that's not the only one, right? You have to imagine there's a lot of disks. They are kind of all stacked on top of each other in this case. And all the way to y equals square root of 2. I'm going to carry on to the next problem. If you don't have any other questions on this. It's not easy, so I really urge you to, later on today or tomorrow, look at those notes.
So we don't need to know dy in the end? After we just integrate it, that'll give us the final answer?
Right, so when you integrate this, the dy it's not like after you find the antiderivative, right? There's no dy anymore. So the dy is already being part of that antiderivative.
Okay.
This means you integrate with respect to y. So this integral notation and the dy, they kind of together. They're like one operation, kind of like a square root with the 2 in the up left corner, or cube root. That's a 3 there. So they're together. It's one operation. So when you perform when you find the antiderivative, that integral and the dy, they all go away. When do we start the quiz? I don't have the answer to this, but if you follow this, you should end up with the correct word. The final answer is not that meaningful for this part. It's all about setting up the question. We're going to start the quiz around 7:30. All right, here's the next question. We're going to find the volume of the solid obtained. Again, we're going to take this shaded region. This is still y equals square root of x. This is x equals 2, y equals 0. But we're going to rotate it about the x equals 0 axis. So x equals 0 is this y-axis. So this is x equals 0. And then we're going to rotate that shape about this axis. Again, I'm going to try to draw that solid after rotation. So the 2 will be mapped to -2. And this point stays at the origin, but this 2 square root of 2 get mapped to this point. So we sort of have this 3D shape. And on top, we also get a 3D shape. So if you try to picture this, on the outside, it's a cylinder, right? So if you take that vertical line, you rotate it around the axis, you get a cylinder on the outside. But inside, in the middle there, you sort of have this like a cone shaped in the middle that's not there, that's empty. So this cone shaped is not there. It doesn't have a solid, it's just a space. So that's a geometry. Right. So if we want a circular cross section, we cannot slice it vertically. Again, we have to do like we did earlier. We have to slice the solid horizontally. And if we slice it horizontally, let's just say this is a one slice. That dotted line is in the back, has a thickness. That thickness, again, is so that disc, because the disc is horizontal, or the washer shape, whatever you call it, is horizontal, so the thickness is in y direction, so that's delta y. In the middle, we also get this circular shape in the middle here. That's not there it's from the cone shape that we take out in the middle. So that's the shape. If you look at it from the top, we have this circular shape, but in the middle we have a part that's missing, this coming from the cone there. And this axis is x equals 0, the y-axis. And then this part will be the cross-sectional area of the solid. Right. So try to picture that in your head. It's not easy, but just do your best to see the geometry. And again, to find the volume, so volume equals integrating from A to B of some area function, but because the thickness is delta y, so we have dy here. That's the thickness. So that means the area function has to be a function of y. So A has to be a function of y. Well, let's find the area function. So the area function, again, the cross section here, just like we had like a couple examples ago, we have it's a washer shape. So we have an outer circle, and then inside we have an inner circle that's missing. So the cross-sectional area is equal to the area of the outer circle minus the area of the inner circle. So I'm going to call the outer circle with a radius R1, and then the inner circle, I'm going to call it radius R2, just like before. So the area would be pi R1 squared minus pi R2 squared. So that's a pi R1 squared minus R2 squared. How do we know AY versus AX? That's a good question. You always decide the area, the independent variable of the area function based on the dy or the dx, the thickness of the slice. If the thickness of the slice is in the x direction, that means in the volume integral you have a dx. So let me write here. So b equals integrating from a to b. If you have a dx there, so that means your area is going to be a function of x. But if you have a dy here, then the area is going to be a function of y. That way you can integrate. If you have a dy, then you have an ax, then you can have a little bit of trouble there. You have to do the conversion. Okay. So that should be the kind of the hint, the matching block. So here, how do we find the large radius, the biggest radius? Well, let's go back to the solid that I draw here. So the biggest radius is the distance going from the blue line, the y-axis, go all the way to that line x equals 2, right? So that's the biggest radius of the entire solid. So this should be R1, the blue line. You agree? So R1 is equal to the distance from the y-axis all the way to x equals 2. So we need to find that distance. And that is given by the value on the right, the x value on the right, which is 2, minus the x value on the left, which is x equals 0. So 2 minus 0. So that's the biggest distance. That's the biggest radius. That's R1. And then next, we're going to find the R2, the radius of the inner circle. That, if you go back to the solid, that's the distance from the y-axis goes all the way to this curve. I draw a small green segment. I hope you can see it. So that's the distance from the function y equals square root of x to the vertical line y-axis. So R2 is equal to distance from y equals square root of x to, you can write as x equals 0, the y-axis, to y equals square root of x. That's the distance for the inner radius, the radius of the inner circle. So, but we're subtracting the two x values, so we cannot use y equals square root of x. So here again, we have to translate this function into x into y squared equals x, or x equals y squared there. And this one is already in terms of x, so x equals 0. This one is x equals y squared, so we're going to find the difference. So R2 is equal to the one on the right. It's given by the square root of x function, so that's a y squared. The one on the left, which is 0, so you get y squared as the radius, the inner radius. And that's going to go into this in the area. So now we can rewrite the area, which is pi times R1 squared, that's a 2 squared, minus R2 squared, which is y squared, squared. So that's a pi times 4 minus y to the 4th. So that's the cross-sectional area function. In terms of y, the last step we're going to put into the volume function. So we got volume is integrating. We're going to find the boundaries a little bit later, but the ay here, which is pi 4 minus y to the 4th dy. But what about the boundaries? Can anyone tell me what the boundaries are for the integral, the lower and upper bound in this case? Square root of 2 and a 0, again, exactly. So because we integrate with respect to y, so you're looking for the y boundaries of the shaded region, right? The shaded region we begin with, the lowest is the x-axis, so that's a y equals 0. The highest, again, just like we had in previous example, the highest given by this point. So that will give you highest y. This is the lowest, sort of the lowest y. So the highest y will be square root of 2, just like we had in the previous example. And I'm not finishing this integral. Any questions about how I find the radius, the two radius here, or how I find the area function? Now, in this case, I hope you kind of can see a bit that the cross section is it's a washer shape, it's horizontal, so that when we find the radius, you have to take the two x values, right, to subtract to figure out the radius. And then when you do that, you have to keep everything in terms of x, like if you have y equals square root of x, you have to translate it into x equals y squared, so you can subtract the two x values. Can you just explain how I got y squared? So I hope you agree with me that for the radius of the inner circle, right, the inner part of that washer shape, the radius is given by the distance from y-axis to the function y equals square root of x. So that's this green segment I have. So that will give me the radius, right? So the distance will be from x equals 0 to y equals square root of x. But since I'm so you imagine this. So here I have an x-axis. So I have x equals 0 here. And I'm looking at this part, which is given by y equals square root of x. So I'm looking for this distance. That will give me the R2. And I cannot just use square root of x directly, because I need to know this y equals square root of x. I need to know this second point in terms of y. So we have to have like an x equals something in order to subtract 0 from it. So to do that, you just take the y equals square root of x, you square both sides. So you got y squared equals x. So the point on the right is x equals y squared. The point on the left is x equals 0. So you can find the distance by using y squared minus 0, the one on the right minus the one on the left. So the y squared coming from square both sides of the equation y equals square root of x to solve for x. Yep. And another thing that you can use as a hint is that because we need the area function to be a function of y, so that means you cannot use y equals something with x directly. You have to rewrite that as x equals something with y. So you have to take all the functions, write it in terms of y first. All right, I'm going to do one more example, and I'll try to finish it, like at least, you know, do the drawing, set up the integral. I'll not take too much time. Oh, actually, that was the end of it. Oh, well. I thought I have another example, but that's a different method. I'm not sure if you're ready for that yet. No? All right, Aiden says no. That's okay. All right, on that note, I'm not going to give you a lot of information, but I think that will give you enough to work on the next homework. You can do, I think there's like probably 4 or 5 questions you cannot work on it yet, which we're going to talk about on Monday. It's the method. It's called the shell method. So yeah, Sam, just a second. So what we have been talking about is what we call a disk method or a washer method, depends on the geometry. So basically you take the solid and then you slice it into circular shapes, right? Circular disk or washer. And then you stack those up, all those disks, you stack them up to get the solid. That's what we did in this part. But the next part is called the shell method. It's basically just like this drawing I have here. If you want to estimate the volume, you kind of take the solid, you imagine there's like a lot of different shells, like a sort of cylinders with a small thickness. So if you imagine that you have a lot of those cylinders, you know, like kind of in the middle, and then outside you have another cylindrical shape, and then another one outside. So each of this cylindrical shape, it's what we call a shell. And then you kind of piece those together. You have one in the middle, and then one next to outside, and another one outside, and so on. So that will give you the solid. So that's called the shell method. We're going to talk about it next time. Trying to introduce the 2 pi thing, and then the different boundary is a little. Okay. Anyway, yeah, so I just want to do the, you know, kind of give you a taste of where we're going. Okay, on that note, all right, on that note, yeah, any questions about, any questions related to the quiz? Sam, any questions, or Christopher?
Yeah, I guess if we could just do like 1 or 2 of the ones I wasn't able to get on the homework, I was having trouble with.
All right. Can you tell me what question was it? I'll look for it.
Yeah, it was question 6. It was the one where it's the integral of e to the cosine 29t times sine 29t.
Okay. All right, I feel like everyone probably have a different number because the values are being
right. Yeah, no, I know.
But just I know okay, I know what you're talking about. Okay, so I think it's this one. Create a new page. So the question is integrating e to the cosine 29t. You probably have a different number for some other people, but it doesn't really matter. And the sine 29t dt. right?
Yep.
So for this one, if you want to find the antiderivative, you kind of have just look at it by inspection. So the e raised to an exponent, that's a function together. You cannot separate. You have to see this as, like one together, one expression. Inside, you have a function that's in the exponent, right? But together, you have to see it as an exponential function. And on the outside, you have the sine part, and then dt. So by just looking at it, looks like sine is the derivative of cosine, right? Derivative of cosine is negative sine, but it's close enough. So it looks like that's the derivative of cosine. So let me finish this and I'll answer more questions related to the quiz. So that means if that part, if sine looks like the derivative of the part in the exponential functions, we're going to have to try to use u-substitution. So we're going to let u equals cosine 29t. Now, I want to point out that u doesn't have to be the part inside the parentheses. So if you set u equals 29t, it probably help you simplify the problem a bit, but it doesn't give you, enough simplification. So keep in mind that u doesn't have to be the part in the cosine, in the parentheses. So here we're going to let u equals cosine 29t. So du equals derivative of cosine is negative sine, using chain rule there. So 29t. And then take the derivative of the inner part, 29t give you 29 dt, using chain rule there. And the solve for dt, which is, we're just going to divide this expression to the left, divide it from both sides. So we got 1 over, actually -1. -1, or actually you can just write 1 over negative sine 29t times 29 du, if you divide it from both sides. After you've done that, you're going to put back into the integral. So that becomes integrating e. Now cosine 29t, that becomes a u, right? Just e to the u. And the sine, let's just leave it. So sine 29t. And then dt becomes 1 over negative sine 29t times 29 du. The benefit of doing that let me finish this problem. The benefit of doing that is that sine we can cancel out. So sine 29t cancels, give you, from the numerator denominator. And then you have 1 over negative 29, which is a constant. We can bring it in front. So we get negative 1 over 29, integrating e to the u du. And the e to the u du is kind of like integrating e to the x dx with just e to the x. In this case, it's e to the u. So you get negative 1 over 29, e to the u plus a c. Don't forget the c here. It's is indefinite integral. And one last step, substitute for the u. So negative 1 over 29, e raised to the u is cosine 29t plus this constant c. This is the antiderivative using u substitution. When you try to find the antiderivative of some expression, if you are not sure how to find it, try u substitution. That might help. All right, here's a few questions. So are we going to, do you need to print out the quiz? No, you don't need to print out. So you don't need to copy down the questions into your notebook when you work out the problem. You can just, just start showing your work. Just make sure you label the work correctly, number 1, solution, number 2, and so on. Just label it correctly. And can we get more time for the quiz? I know you probably feel a bit anxious about not being able to finish it. Don't worry. I'm confident that you have enough time on the quiz. I don't think it's going to be too long. So half an hour should be enough. You know, worst case, if no one finish it in half an hour, then we can, you know, decide what to do after that. But for now, don't worry about it. So yeah, so you only get, you know, the amount of time you get, half an hour. Everyone got the same amount of time. So you get half an hour to work on the quiz, and then after that, you get extra 10 minutes to scan your solution and upload it onto Canvas. So in total, you get 40 minutes, right? So if you have accommodations that I'm aware of, depends on what it says. So I give you more time accordingly. So you don't need to worry about that if you do have accommodations. But if you never told me about it and I didn't receive any information about it, wow, you just have to deal with it this time, and next time let me know in advance. I know that the 2 people have extended time. All right, is the quiz going to be on Gradescope? No, it's not. It's just going to be on Canvas. I'll show you in a few minutes where to find. There's a few places you can find the quiz. I'll show you. I have not published the quiz yet, so you can't see it. All right, I think there was someone says, can we go over a few questions about can we go over a few problems that may be related on the quiz? No, because I don't want to go over, you know, questions that might give you hints about what kind of problems might be on the quiz. But quiz questions are similar to examples that we go over in lectures and also the homework questions. So if you feel good about those homework questions and lecture questions, then you should be prepared. All right, any other questions about the homework? We can spend more time on that. All right, so they meant just homework questions. That's okay. We can go over a few more homework questions.
Yeah, I have one.
No, go ahead.
It's the integral of 5x squared plus 4 plus 3 over x squared plus 1.
5x squared plus
3 over x squared plus 1. It's 3 over x squared plus 1. Yeah.
This one.
Yep.
Okay.
Thought I knew how to do it, but I got it wrong. So.
Okay. So you're good with the first 2 terms when you find the antiderivative, right?
Yep.
You can just separate the integral as integrating each term. So integrating the first term, 5x squared dx, plus the integral of 4 dx, plus the integral of 3 over x squared plus 1 dx. And then the next step is pull out all the constant coefficients. And in the last term, I'm going to pull out this 3 because it's kind of a 3 times a 1 divided by something. So that's a 5 integrating x squared dx plus 4 integrating 1 dx, just 1 dx, plus 3 times integral 1 over x squared plus 1 dx. And the first term, you still have 5 there, but when you integrate, you add 1, so that's x cubed divided by 3, so that's a 5 over 3, plus 4 times integral of dx is just x, plus 3 times, now the last integral is a special one. If you look into 5.4 in the table, when you integrate 1 over x squared plus 1, you get inverse tangent of x. So arctan of x, that's another way to put it. And then don't forget to add a constant c at the very end.
Yeah, I just forgot the 3 in front of tan.
Okay. So yeah, so that's so I always, any constant I have in the numerator, if it's just a constant, I always bring it in front. It just basically is 3 times 1. The 3 can always go to the front. Good. Any other questions? Oh, by the way, I want to mention this. So for all the homework questions, you can try it 100 times, right? If you get something wrong, don't give up, right? Just, after you submit your work or however, I don't know, you get a feedback immediately tell you did it wrong. Just keep, look at the question, look at your work, try to figure out where you got it wrong. And you can try it a lot of times. It depends on I guess, I thought I give you 100 tries on each problem, but I guess some teachers give you 10 tries. If you try 10 times and you cannot put in more answers, if you reach the limit, let me know. Okay, yeah, so right, so right. But I just want you to I want you to try and I want you to figure out the answers, right? So yeah, so I give you a lot of time. So don't be afraid of like making mistakes when you put in solution there. But obviously don't guess it, right? So if you keep guessing, it probably doesn't help you much. So don't worry about making mistakes. Put the solution in there. Doesn't work, try something a little bit different, or look at the work, try to find the mistakes. Any other questions? Any questions about finding area between curves? Like if you have, let's see if I have a question here that I can dig out. Oh, I did not give you oh, you know what? I did not give you a question on the area between curves. Let's see. How about this one? Find area enclosed by function. Just see y equals x squared and y equals x. Make it simple. So obviously you're going to graph this. Like I said, you can use decimals.com or calculator to graph it, but just make sure if you do use something to graph it, copy the graph onto onto your notebook, so I know what the graphs are. So y equals x squared, I know it's going to be this shaped, and the y equals x is something that looks like this. And obviously we want an enclosed area, right? So we wouldn't take anything on the left because that's not a closed region. The closed region is from here to there. That's a straight line, y equals x, and the y equals x squared. That's the enclosed region. And we're looking for that area. That's a couple ways. This is a y equals x squared. So remember to find the area of, look for any array. You can divide it into rectangles. So here, I'm going to use a vertical rectangle first. So if you draw a vertical rectangle, and then this small rectangle has the thickness, the base, it's just how wide it is. That base is delta x, right? Just by looking at that segment at the bottom. So that's a base. And the height of the rectangle is given by the distance between those two functions. If you recall that the area is equal to the integral from a to b of the height of the rectangle times the base of a rectangle. The base in this case is delta x. I'm going to put dx there. The height of the rectangle is given by the difference between the two functions. The higher function minus the lower function. So that in this case, it's f higher minus f lower. So the higher function is y equals x. The lower function is y equals x squared. Because it's dx, so the height is a function of x. So we're going to write x minus x squared to give us the height, the difference between the two y values. Right? So that will, and then you just have to figure out the boundaries. Well, if you plot this in decimals, you can immediately figure out the intersection. This is a 0, 0, and at this point is a 1, 1. So since we integrate with respect to x, we need to know the x boundaries. The x boundary for this region is going from x equals 0 to x equals 1. So that will be from 0 to 1. So those are the boundaries of integral. Questions on that? So that's using a vertical rectangle. Of course, that's not the only way. You can use a horizontal rectangle. So if you draw the horizontal rectangle here, I'm going to use the red color. So this horizontal rectangle, when you draw it, that rectangle has a thickness delta y. So the area is equal to some integral of some function for height. Well, not the height. In this case, will be the base of the rectangle, because the thickness, the height of the rectangle is delta y. So dy. So this part has to be a function in terms of y, because we have a dy there. Well, let's find out the base of this horizontal rectangle. That's between the function on the right minus the function on the left. So this is given by function on the right minus the function on the left. The function on the right is that y equals x squared. The function on the left says y equals x. But I can't just use x squared and x directly. I have to use function of, I have to turn them into x in terms of y, because I have a dy there. So I have to, so cannot use directly, because I need like something with y into that parentheses. So I have to rewrite it. Y equals x squared. I have to find the x. So x takes square root. So x equals square root of y. That's what we're going to use. And the y equals x, the same thing as x equals y, so we can use that directly. So when we find the base of the rectangle, the function on the right, we're going to use square root of y. The function on the left is just y. So square root of y minus y, that gives us the base of the horizontal rectangle. And the boundaries for the integral, we're going to have to use the y values in this case, not x values. So here we have to use the y values. The lowest y for that region is y equals 0. And the highest y is y equals 1. So that's going from 0 to 1. This is sort of like, to find the boundary is sort of the same way that we did it with the volumes, right? And then the rest is about integrating and find the antiderivative, plug in the boundary values to find the area. Will something like this be on the quiz? Yes, there'll be something like this on the quiz. This is a 6.1 area between curves. You can choose either method. You can draw the. It's always good to have the region available and then draw just one rectangle, either a horizontal rectangle or vertical rectangle. That will help you identify the delta x or y. Depends on how you draw the rectangle, and also helpful when you try to find the boundaries for equation. All right, let's see, any other questions that I should mention? that was a one question in the homework that was integrating sine t square root 1 plus cosine t dt. This one is just like the very first question Christopher asked. So you're gonna have to use u-substitution because it looks like a sine of t is the derivative of 1 plus cosine of t, right? Because a 1, when you take the derivative, becomes 0. So you're gonna have to use u-substitution by letting u equals 1 plus cosine t. And then take the derivative du equals negative sine t dt. And then solve for dt there, which is 1 over negative sine t du. When you put this into the integral, well, right, how do you know? Well, one of the hint is to look for the derivative, right? If one part seems to be the derivative of some inner function, so you can try to use u-substitution. Another way is you just look at it. If I give you this, we really don't know how to integrate this using the rules we know, because this is the product, right? It's a product between two functions. We just don't know how to integrate a product yet without using u-substitution. So your best chance is just, since no other method that we know could work, just try with u-substitution and see if it helps. At least try that. Anyway, so this part I'm not going to finish. So if you put in there, and then you should be able to simplify quite a bit and then integrate. A similar question would be, let's say if you're integrating, let's see, fifth root of, let's just see, you have 10x minus 2 squared dx. Oh, okay. All right. Yeah. Okay. So I give you this example. Think about it. Let me finish the previous problem. So now let's plug in. So that's integrating sine of t. Just leave it. Sine of t and the square root. Just square root. But inside the square root we have a u. And the outside dt becomes a 1 over negative sine t du. Right. That's just substituting for the 1 plus cosine t and a substitute for dt. And the good thing here is that those terms cancel out. And they give us a -1 in front. So that's a negative integrating square root of u du. And I'm going to write square root of u as u to the half, which make it a lot easier. So that's a negative u to the half. When you integrate, that becomes u to the 1/2 plus 1, that's a 3/2, but you have to divide by the new exponent 3/2, so that's a 1 over 3/2 plus a constant. So that's a negative 2 over 3 u to the 3/2 plus a constant. Don't forget to substitute for the u. 2 over 3, u is 1 plus cosine t to the 3/2 plus a constant.
Thank you.
Yeah. How about this new one I wrote? Well, you have a fifth root, and then you have a square underneath the root. And inside you have a 10x minus 2, right? It looks complicated. I don't know how to integrate using the, using the power rule or using the special rules in the table. So what we're gonna do? Well, I don't know, but let's try with u-substitution, right? Even though it looks like there's no product, but I can imagine there's a 1 in front of it. I can imagine that's a constant 1. And it seems like if I differentiate 10x minus 2, I get a constant. So the 1 seems to be a multiple of the derivative. Not exactly the derivative, right? But it's the 1 and the derivative of 10x minus 2 is the same type of expressions or functions. They're similar, so I'm just going to assuming that 1 is a derivative because there's no other way I know I can integrate. So I'm just going to try with u-substitution. Try u-substitution. I'm going to let u equals 10x minus 2. You probably wonder, can we try with 10x minus 2 squared? Well, you can try that, but then you kind of introduce a new term. It may work, but it's not straightforward. So I'm going to try with u equals 10x minus 2. So du equals 10 dx. Even though it's a 10, but it's just a constant times dx. And then dx equals 1 over 10 du. And if I using this in the integral, so I get integrating 5th root of u squared dx becomes 1 over 10 du. See, it doesn't really change anything. So the 1/10 I can bring in front. So I get 1 over 10 integrating 5th root of u squared. So that's a u to the in the exponential form, the 5th root become a denominator, and the power become the numerator. So u to the 2/5 u. And from there, you know how to integrate. Just again, add a 1 to the exponent, divide by the new exponent. So that's u to the 2/5 plus 1, that's a 7/5. And then divide by the new exponent, so divide by 7/5. So that's 1/10 divided by 7/5 times 5 over 7. U, which is 10x minus 2 to the 7 over 5th power plus c. Simplifies that constant a bit more. So that's a 1 over 14 x minus 2 to the 7/5. I just want to use this example to show you that, when you need to integrate something, you feel like you don't know what to do at this point, you try with u-substitution. Take one part of it, set it equal to u, and to see if that helps. You might have to try different parts.